Witnessing creation, the first photo of a planet being born. Dr. Miriam Kepler sits alone in the control room of the European Southern Observatory, her eyes fixed on the screen as data streams in from the SPHERE instrument attached to the Very Large Telescope in Chile. It's 2:47 a.m. in Munich, July 2018, and she's been awake for 20 hours straight. But sleep is the last thing on her mind. The image building pixel by pixel on her screen shouldn't exist. For decades, astronomers have theorized about how planets form, created elaborate computer models, studied indirect evidence, but no one has ever actually seen it happening, until now. There, in the disk of dust and gas surrounding the young star PDS-70, is a bright point of light that shouldn't be there. Not a star, not a glitch, not an artifact of the imaging process. It's a planet, still glowing from the heat of its own formation, still gathering material from the surrounding disk, still becoming what it will be. She runs the data processing again and again. The bright spot remains, sitting in a gap in the disk exactly where theory predicted a forming planet should be. Her hands shake as she reaches for her phone to call her colleague André Muller. "André," she says when he answers groggily, "you need to see this. We have it. We actually have it." "Have what?" he mumbles. "A photo of a planet being born." The silence on the other end stretches for several seconds. Then, "I'm on my way." What Kepler discovered that night, later confirmed as the planet PDS-70b, was revolutionary enough. But it was just the beginning. By 2025, with the combined power of the James Webb Space Telescope and ALMA, Atacama Large Millimeter Array, we wouldn't just see one baby planet. We'd witness an entire planetary system in the act of creation, capturing details that overturn decades of assumptions about how worlds like Earth came to be. This isn't just a story about finding another planet. It's about witnessing creation itself, the fundamental process that turns cosmic dust into worlds, chemistry into geology, potential into reality. For the first time in human history, we can watch the universe building new homes for possible life. To understand what makes the PDS-70 discovery so revolutionary, you first need to understand what we thought we knew about planet formation, and how wrong we might have been. The classical model, developed over centuries of observation and theory, painted a relatively simple picture. A cloud of gas and dust collapses under its own gravity. The center becomes a star. The leftover material flattens into a disk. Within this disk, dust grains stick together, growing from pebbles to boulders to planetesimals to planets. It's cosmic accretion, the gradual accumulation of material over millions of years. This model explained a lot. It told us why planets orbit in the same direction, why they're mostly in the same plane, why rocky planets form close to stars while gas giants form farther out. It was elegant, logical, and almost certainly incomplete. The problem with our models, explains Dr. Sean Andrews at the Harvard-Smithsonian Center for Astrophysics, is that they were based on our single example, our own solar system, 4.6 billion years after the fact. It's like trying to understand human development by only studying adults. You can infer a lot, but you miss the messy, chaotic, wonderful reality of actual growth. PDS-70 changed everything, because it let us watch that messy reality in real time. Located 370 light-years away in the constellation Centaurus, PDS-70 is a young star, only 5.4 million years old. In cosmic terms, it's a newborn itself. Our Sun, by comparison, is 4.6 billion years old, solidly middle-aged. Around PDS-70 swirls a protoplanetary disk, a cosmic pancake of gas and dust 140 astronomical units across, more than twice the distance from our Sun to Neptune. Within this disk, planets are actively forming right now. Not millions of years ago, not in some theoretical model, right now, as we watch. The first confirmed planet, PDS-70b, sits about 22 astronomical units from its star, roughly Uranus's distance from our Sun. It's a giant, several times Jupiter's mass, and it's still glowing at about 1000 degrees Celsius from the heat of its formation. But here's where it gets interesting. The planet has carved a visible gap in the disk, and it's actively pulling material from the surrounding dust and gas. We can see streams of material flowing onto the planet, watch it growing before our eyes. In 2019, astronomers found a second planet, PDS-70c, orbiting at about 34 AU. Together, these two planets have cleared a massive gap in the disk, and they appear to be sharing material between them, a cosmic dance of creation we never imagined we'd witness. Dr. Julian Girard at the Space Telescope Science Institute puts it in perspective. Every single planet in the universe, including Earth, went through this phase. But this is the first time we've caught one in the act. It's like having a time machine that lets us watch our own origins. Photographing a forming planet should be impossible. The challenge is like trying to spot a firefly next to a searchlight from 1,000 miles away. The star's glare overwhelms everything around it. The planet is 1 billion times fainter. The dust disk scatters light in all directions, and we're trying to see details smaller than what conventional optics should allow. The breakthrough came from a combination of technologies that sound like science fiction. Adaptive optics. Earth's atmosphere is constantly moving, blurring celestial images. The Very Large Telescope's adaptive optics system uses lasers to create artificial guide stars, then deforms its mirrors up to 1,000 times per second to counteract atmospheric turbulence. The result is images nearly as sharp as if the telescope were in space. Coronagraphy. To block out the star's overwhelming light, astronomers use a coronagraph, essentially an artificial eclipse inside the telescope. The Sphere instrument's coronagraph is so precise it can block 99.99% of a star's light while leaving the surrounding area visible. Polarimetry. Light from the star is unpolarized, but light reflected off dust grains in the disk becomes polarized. By filtering for polarized light, astronomers can make the disk appear to glow while the star's direct light vanishes. Interferometry. ALMA doesn't use a single telescope, but 66 antennas working together as one massive instrument. By combining signals from all antennas, ALMA achieves resolution equivalent to a telescope 16 kilometers across. Dr. Miriam Benisti at the University of Grenoble, who led many of the ALMA observations, explains the challenge. We're not just taking a picture, we're reconstructing reality from incredibly faint signals, using every trick physics allows. Each image represents hundreds of hours of observation and thousands of hours of data processing. The James Webb Space Telescope, operational since 2022, added a new dimension to these observations. Its infrared vision can peer through dust that blocks visible light, revealing hidden structures within the disk. Its coronagraphs are even more sophisticated than ground-based versions, and from its position at the L2 Lagrange point, it avoids atmospheric interference entirely. In 2025, JWST's observations of PDS-70 revealed something extraordinary. The planets aren't just forming from the disk, they have their own mini-disks around them, called circumplanetary disks. These are the birthplaces of moons. We're not just watching planets being born, we're watching entire moon systems forming around those planets. Dr. Christophe Pinte at Monash University, who predicted circumplanetary disks before they were observed, describes the discovery. It's like zooming in on a pregnancy and discovering the baby is pregnant too. These nested disks within disks show us that moon formation happens simultaneously with planet formation, not sequentially as we thought. The GDSF, the technical achievement is staggering. We're resolving structures a few astronomical units across, from 370 light-years away. That's like reading the date on a coin in New York from Los Angeles. And we're not just seeing these structures, we're measuring their temperature, composition, velocity, and magnetic fields. What ALMA and JWST revealed about PDS-70 isn't just images, it's chemistry. For the first time, we can analyze the actual material from which planets are forming. The results are rewriting our understanding of planetary composition. The disk around PDS-70 isn't uniform. ALMA detected over 20 different molecules, including water, methane, carbon monoxide, hydrogen cyanide, and complex organics. But here's the surprise. These molecules aren't evenly distributed. They're concentrated in rings and spirals, creating chemical zones where different types of planets might form. Dr. Karin Erberg at Harvard, who studies disk chemistry, explains the significance. We always assumed planets inherited their composition from wherever they formed in the disk, but PDS-70 shows planets actively selecting what they incorporate. They're not passive recipients of material, they're active participants in their own creation. The forming planets are surrounded by hot gas that makes them glow in specific wavelengths. By analysing this light, astronomers can determine what the planets are made of as they form. PDS-70b shows strong signatures of water vapour and carbon monoxide in its atmosphere, molecules that will determine its eventual climate and potential habitability of any moons. But the real revelation came from isotope analysis. Isotopes are versions of elements with different numbers of neutrons. They form in different conditions and can tell us where material originated. The isotope ratios in PDS-70's disk don't match what we'd expect from local material. Some of the dust and gas came from interstellar space, carrying material from other star systems, even other galaxies. Every forming planet is a mixture of local and imported ingredients, says Dr. Conal Alexander at the Carnegie Institution. Earth's water might have come from interstellar ice that travelled between stars for millions of years. The carbon in our bodies might have formed in stars that died before our sun was born. PDS-70 shows us this mixing happening in real time. The temperature structure of the disk creates a cosmic chemistry set. Close to the star, it's hot enough to vaporize rocks. Farther out, water freezes into ice. Even farther, methane and carbon monoxide freeze. These snow lines determine what materials are available for planet formation at different distances. JWST revealed that PDS-70's snow lines are dynamic. They move as the star's brightness varies and as forming planets heat their surroundings. A planet forming just inside the water snow line might suddenly find itself surrounded by ice as conditions change, dramatically altering its composition. Dr. Edwin Bergin at the University of Michigan has modelled this process. It's not like baking a cake with fixed ingredients. It's like the ingredients keep changing while you're mixing them. A planet might start forming as a dry, rocky world, then suddenly acquire massive amounts of water as the snow line moves past it. The organic chemistry is particularly intriguing. JWST detected complex carbon chains, including molecules that could be precursors to amino acids. These organics aren't rare. They're throughout the disk, constantly being created by the interaction of stellar radiation with simpler molecules. We're watching the universe set the table for life, says Dr. Karin Erberg. The same processes creating planets at PDS-70 are creating the organic molecules life needs. Planet formation and prebiotic chemistry aren't separate processes, they're two aspects of the same cosmic event. The classical picture of planet formation was almost serene, dust gradually accumulating over millions of years. PDS-70 reveals a far more violent reality. Planet formation is a chaotic, competitive process where timing is everything, and most contestants don't survive. The disk around PDS-70 isn't smooth. It's full of gaps, rings, spiral arms, and vortices. Each structure tells a story of gravitational warfare. The two confirmed planets have cleared a massive cavity in the disk, but JWST revealed this cavity isn't empty. It's full of smaller bodies fighting for survival. Dr. Ruoving Dong at the University of Victoria has modelled these dynamics. It's like a cosmic Hunger Games. Thousands of planetesimals form, but only a few will become planets. The rest will be eaten by their siblings, ejected from the system, or torn apart by gravitational forces. The violence is visible in real time. In 2024, astronomers observed a bright flash in the disk, likely a collision between two planetesimals, each hundreds of kilometers across. The impact released more energy than 1 billion nuclear weapons, vaporizing both bodies and creating an expanding cloud of dust that temporarily brightened that section of the disk. We used to think impacts were rare accidents, explains Dr. Zoe Leinhardt at the University of Bristol. But PDS-70 shows us they're the norm. Planet formation is fundamentally destructive. Worlds must die for other worlds to be born. The gravitational interactions are equally dramatic. The two giant planets engage in a celestial dance called mean motion resonance. Their orbital periods are locked in a precise ratio. This resonance creates waves in the disk, like cosmic tsunamis of gas and dust. These waves can either feed material to forming planets or strip it away, determining which worlds grow and which starve. ALMA observations revealed something unexpected. The planets are migrating. PDS-70b and C aren't where they originally formed. They're moving through the disk, their gravity creating wakes like ships through water. This migration can be inward or outward, fast or slow, smooth or catastrophic. Dr. Frederic Massé at the National Autonomous University of Mexico has studied planetary migration for decades. PDS 70 confirms our worst fears and greatest hopes. Planets don't stay put. They wander through their systems, potentially destroying everything in their path or shepherding smaller bodies into stable orbits. A planet forming in one location might end up anywhere. This migration explains one of astronomy's biggest mysteries: hot Jupiters. These gas giants orbit closer to their stars than Mercury orbits our Sun. They couldn't have formed there, it's too hot. They must have formed farther out and migrated inward. PDS 70b might be in the early stages of such a journey. The violence extends to the stellar level. Young stars like PDS 70 are unstable, prone to outbursts that can strip atmospheres from forming planets or blast gaps in the disk. In 2025, JWST captured one such outburst, a stellar flare that temporarily increased PDS 70's brightness by 30% and sent shockwaves through the disk. These flares might seem destructive, but they're also creative, notes Dr. Ilaria Pascucci at the University of Arizona. They can trigger gravitational instabilities that speed up planet formation. They can vaporize ice, changing disk chemistry. They might even be necessary. Without stellar outbursts, disks might be too stable for planets to form efficiently. The turbulence in the disk creates vortices, cosmic whirlpools that can trap dust and accelerate planet formation. ALMA imaged several vortices in PDS 70's disk, each potentially nursing a future planet. But vortices are unstable. They can merge, split, or dissipate suddenly, dooming any planets forming within them. Perhaps the most stunning discovery at PDS 70 was the confirmation of circumplanetary disks, mini-disks around the forming planets where moons are being born. It's a fractal process, disks within disks, creation within creation. The circumplanetary disk around PDS 70c was first hinted at in 2019, but JWST's 2025 observations revealed it in stunning detail. The disk is about 1 astronomical unit across, the distance from Earth to the Sun, but only a few hundred kilometers thick. Within this disk, material spirals inward toward the planet, while moons form in the outer regions. Dr. Judith Żulaji at ETH Zurich, who predicted circumplanetary disks before they were observed, describes their importance. These disks are why Jupiter has 95 moons while Mars has only 2. They're factories that can produce entire moon systems in just a few million years. The temperature structure of circumplanetary disks creates their own snowlines, just like the main disk. Close to the planet, it's hot enough to vaporize rocks. Farther out, ice moons can form. This explains why Jupiter's inner moons are rocky, while its outer moons are icy. They formed on different sides of the snowline. JWST detected water, ammonia and methane in PDS 70c's circumplanetary disk, the ingredients for moons that could potentially harbour subsurface oceans like Europa or Enceladus. The disk also shows organic molecules, suggesting that moons forming there might be seeded with prebiotic chemistry. We're not just watching a planet form, emphasises Dr. Robin Canup at the Southwest Research Institute. We're watching the birth of potentially habitable moons. If PDS 70 Sense ends up with moons like Europa, they could have subsurface oceans capable of supporting life. The dynamics of moon formation are surprisingly violent. Moons compete for material just like planets do. They collide, merge, and sometimes get ejected from the system entirely. ALMA detected several gaps in PDS 70c's circumplanetary disk, likely cleared by forming moons. In 2025, astronomers may have witnessed moon formation in action. A bright spot appeared in PDS 70c's circumplanetary disk, persisted for several weeks, then faded. The most likely explanation: a large moon forming through gravitational instability, essentially collapsing directly from the disk rather than growing gradually. Dr. Konstantin Batygin at Caltech models these processes. Gravitational instability can form moons much faster than we thought, in thousands of years rather than millions, but these moons are born hot and violent. They might explain why some moons show evidence of early catastrophic melting. The interaction between the planet and its circumplanetary disk is complex. The planet's magnetic field threads through the disk, creating electric currents that heat the material and might even launch jets, miniature versions of the jets seen from forming stars. It's electromagnetic birth control, explains Dr. Xiaohuan Zhu at the University of Nevada. The magnetic fields can either help or hinder moon formation, depending on their strength and configuration. Too strong, and they prevent moons from forming. Too weak, and the disk becomes unstable. The feeding process is particularly fascinating. Material from the main disk doesn't fall directly onto the planets. Instead, it flows onto the circumplanetary disks, which then feed the planets. JWST captured streams of gas flowing from PDS-70's main disk onto both planets' circumplanetary disks, cosmic umbilical cords feeding the growing worlds. The discoveries at PDS-70 force us to reconsider how our own solar system formed. The neat, orderly process we imagined, with planets forming in their current locations over millions of years, is almost certainly wrong. Dr. Alessandro Morbidelli at the Observatory of Nice has spent his career modelling solar system formation. PDS-70 shows us that our ideas were too simple. The early solar system was probably far more chaotic, with planets migrating dramatically and entire worlds being destroyed. Consider Jupiter. We thought it formed roughly where it orbits now, but PDS-70 suggests gas giants form quickly and migrate significantly. The Grand TAC model proposes that Jupiter formed at about 3.5 astronomical units, migrated inward to 1.5 astronomical units, where Mars orbits now, then reversed course and migrated back out to its current position at 5.2 astronomical units. This migration would have been catastrophic for any planets in Jupiter's path. It might explain why Mars is so small. Jupiter stole its building materials. It might also explain the asteroid belt. Debris from worlds Jupiter destroyed during its journey. Jupiter was a wrecking ball swinging through the early solar system, says Dr. Kevin Walsh at the Southwest Research Institute. Without that violence, Earth might never have formed as we know it. Earth's water is another mystery that PDS-70 helps illuminate. Earth formed inside the water snowline, where it was too hot for water ice to condense. So where did our oceans come from? PDS-70 shows that snowlines move, and that planets can acquire materials from across the disk through migration and scattering. Dr. Connell Alexander explains, Earth's water probably came from multiple sources, some from water-rich asteroids scattered inward by Jupiter, some from comets, some possibly from the solar nebula itself. PDS-70 shows us these delivery mechanisms in action. The Moon's formation takes on new significance in light of circumplanetary disks. While our Moon probably formed from debris after a Mars-sized planet hit Earth, PDS-70 shows that large moons can also form directly in circumplanetary disks. Some of Earth's early companions might have formed this way, before being lost to collisions or ejection. The timeline is perhaps the biggest revision. We thought planet formation took tens of millions of years, but PDS-70's planets formed in just a few million years, and they're still growing. Gas giants might form even faster, perhaps in just hundreds of thousands of years, through gravitational instability. Earth might have formed much faster than we thought, suggests Dr. Sarah Stewart at UC Davis. The late veneer of materials that brought water and organics might have arrived while the planet was still partially molten, not millions of years later, as we assumed. The violence observed at PDS-70 also explains some of solar system's weird chemistry. Calcium-aluminum inclusions, Ca1s, in meteorites formed at extremely high temperatures near the Sun, yet they're found in asteroids that formed in the outer solar system. PDS-70 shows how stellar outbursts and disk winds can launch material from the inner disk to the outer regions. Dr. Steve Desch at Arizona State University has modelled this process. The early solar system was like a snow globe being shaken. Material from everywhere ended up everywhere else. That's why we find stellar debris in comets and comet dust on Earth. The ultimate question about PDS-70 is whether we're witnessing the birth of habitable worlds. Could PDS-70b or c develop into something Earth-like? Or are we seeing the formation of alien worlds unlike anything in our solar system? The current planets at PDS-70 are gas giants, far more massive than Earth. But that doesn't mean the system won't eventually have terrestrial planets. Dr. Sean Raymond at the University of Bordeaux has run simulations of PDS-70's future. The gas giants are just the first act. After the disk dissipates, leftover planetesimals will continue colliding and merging for another 100 million years. Rocky planets like Earth form from these late collisions. PDS-70 might eventually have Earth-like planets closer to the star. The habitable zone around PDS-70, where liquid water could exist, extends from about 0.7 to 1.4 AU from the star. This region currently appears empty in our observations, but it's likely full of smaller bodies we can't yet detect. These could merge to form terrestrial planets over the next 100 million years. More intriguingly, the moons forming around PDS-70b and c might themselves be habitable. If these planets migrate inward to around 1 to 2 astronomical units, their large moons could have Earth-like temperatures. With water already detected in the circumplanetary disks, these moons could have oceans. Dr. Lisa Kaltenegger at Cornell has modelled potentially habitable moons. A large moon around a gas giant could be even better than Earth for life. The planet's magnetic field would protect against stellar radiation. Tidal heating would maintain geological activity. You'd have stable, long-term habitability. But PDS-70 might be creating entirely new types of worlds. The complex chemistry in the disk, with regions enriched in different molecules, could produce planets with compositions impossible in our solar system. We might see super-Earths with hydrocarbon oceans, carbon planets with diamond mantles, or water worlds completely covered in ice, speculates Dr. Diana Valencia at the University of Toronto. PDS-70 is experimenting with planetary recipes we've never imagined. The organic molecules detected throughout PDS-70's disk are particularly intriguing. These complex carbon chains are being incorporated into forming planets and moons. Whatever worlds emerge will be seeded with the building blocks of life from day one. Dr. Pascal Ehrenfreund at George Washington University studies organics in planet formation. Life on Earth had to create its own organic molecules from simple ingredients, but worlds forming at PDS-70 are born with an organic chemistry set already in place. They could have a huge head start on developing life. The stellar environment matters too. PDS-70 is a K-type star, slightly cooler and smaller than our Sun, but more stable. K-stars have less harmful UV radiation and longer lifespans than Sun-like stars. If PDS-70 develops habitable planets, they could remain habitable for 20 to 30 billion years, far longer than Earth. K-stars might be the sweet spot for life, argues Dr. Jada Arni at NASA Goddard. They're stable enough for complex life to evolve, but active enough to drive atmospheric chemistry. PDS-70 might be creating some of the best real estate in the galaxy. The system's architecture could also enhance habitability. The two giant planets might act as shields, deflecting comets and asteroids that could otherwise bombard inner terrestrial planets. Jupiter plays this role in our solar system, and PDS-70b and c could do the same. PDS-70 isn't unique. It's one of hundreds of young stars with protoplanetary disks that we can now observe. Each one is a laboratory for planet formation, and together they're revealing the incredible diversity of planetary systems. ALMA has surveyed dozens of protoplanetary disks, finding an amazing variety of structures. Some have single planets carving clean gaps. Others have multiple planets creating complex patterns. Some show spiral arms, suggesting planets we can't yet see. Others have rings and gaps with no visible planets at all. Every disk is different, says Dr. Sean Andrews. We expected to find a standard template for planet formation, but instead we're finding that every system is unique. The universe is more creative than we imagined. The Taurus star-forming region, just 400 light-years away, contains dozens of infant star systems. JWST's survey revealed that about 70% have disks massive enough to form planetary systems. Planet formation isn't rare, it's the norm. Dr. Joan Najita at NOIR Lab has catalogued disk properties. We're finding that planet formation is incredibly robust. It happens around binary stars, in stellar clusters, around stars of all masses. The universe seems determined to make planets everywhere possible. Some discoveries challenge our basic assumptions. GW Orionis, a system with 3 stars and a warped, broken disk. Planets forming there would have 3 suns and wildly varying seasons. AB Aurigae shows a spiral structure suggesting a massive planet forming at 93 astronomical units from its star, 3 times Neptune's distance. It shouldn't be possible to form planets that far out, yet there it is. HD 163296 has 3 planets creating a bullseye pattern of rings and gaps so perfect it looks artificial. It's showing us that some planetary systems can achieve extraordinary orbital harmony. DM Tau, a disk that should have dissipated millions of years ago but hasn't, suggesting some disks can sustain planet formation far longer than expected. The chemistry varies wildly between disks. Some are water-rich, others carbon-rich. Some have abundant organics, others are surprisingly sterile. This chemical diversity means the galaxy is creating an incredible variety of planetary compositions. Dr. Ilaria Pascucci notes, "We're not seeing planet formation, we're seeing planet formations, plural. There might be as many ways to make planets as there are stars. Each system is an experiment in world building. The timescales vary too. Some stars form planets in 1 million years, others take 10 million or more. Some create many small planets, others a few giants. Some systems are dynamically violent, others remarkably peaceful. This diversity has profound implications for life. If there's no standard way to make planets, there's no standard type of habitable world. Life might be possible in configurations we never imagined. The technology to observe planet formation is advancing at breakneck speed. What we've learned from PDS-70 is just the beginning. The next generation of instruments will reveal planet formation in unprecedented detail. The Extremely Large Telescope, ELT, coming online in 2028, will have resolving power that dwarfs current telescopes. Its 39-meter mirror will be able to see individual forming planets in dozens of systems, tracking their growth in real time. Dr. Marcus Kasper at ESO, who's developing ELT instruments, describes the capabilities. We'll be able to see planets as small as Earth forming in nearby systems. We'll watch moons forming around giant planets. We'll track chemical changes as worlds evolve. It will be like having HD video of planet formation instead of blurry snapshots. The Nancy Grace Roman Space Telescope, launching in 2026, will survey thousands of young stars simultaneously. Using coronagraphy even more advanced than JWST's, it will create a census of forming planetary systems across the galaxy. Roman will give us statistics, explains Dr. Bruce McIntosh at Stanford. Instead of studying individual systems, we'll see patterns across hundreds of systems. We'll finally understand what's normal and what's unusual in planet formation. The Square Kilometre Array, SKA, a radio telescope being built in Australia and South Africa, will detect the magnetic fields of forming planets. This will reveal how planets generate magnetic fields, crucial for habitability, and how these fields affect moon formation. Dr. Evgenia Shkolnik at Arizona State University studies stellar planetary magnetic interactions. Magnetic fields are the invisible hands shaping planet formation. SKA will let us see these hands at work, understanding how planets become magnetically active and how this affects their evolution. But perhaps the most exciting development is the proposed Habitable Worlds Observatory, HHWO, tentatively planned for the 2040s. This would be a super JWST, specifically designed to image Earth-like planets around nearby stars, including young systems where such planets are still forming. HWO could watch Earth-like planets being born, says Dr. Natalie Batala. We could see their atmospheres developing, their surfaces cooling, their oceans condensing. We could witness the conditions for life emerging on other worlds. Machine learning is revolutionizing how we analyze the massive datasets from these observations. AI can now identify forming planets in disk images that humans miss, predict where planets will form before they're visible, and even determine planetary compositions from subtle disk chemistry. Dr. Inga Kamp at the University of Groningen develops these AI tools. We're teaching computers to see patterns humans can't perceive. The AI has already found candidate planets in archival data that we overlooked. It's becoming our partner in discovery. Laboratory experiments are also advancing our understanding. Scientists can now recreate protoplanetary disk conditions in the lab, watching dust grains stick together in microgravity, studying how ices form on dust particles, and testing how organic molecules survive planet formation. Dr. Jürgen Blum at TU Braunschweig conducts these experiments. We're bringing planet formation down to Earth, literally. We can test specific processes, verify our models, and discover new phenomena that we then look for in real disks. As I write this, imagining the view from 2025, PDS-70 has become more than just another astronomical discovery. It has become a mirror for humanity to see its own origins, a window into the fundamental creativity of the universe, and a reminder of our cosmic heritage. Every atom in our bodies, except hydrogen, was forged in stars. The carbon in our DNA, the iron in our blood, the calcium in our bones, all were once dust grains in a disk like PDS-70's, slowly gathering to build a world. We are, quite literally, made of stardust that once swirled in a protoplanetary disk 4.6 billion years ago. Dr. Carl Sagan famously said, "We are star stuff contemplating the stars." But PDS-70 lets us be more specific. We are planet stuff watching planets being made. We are the universe observing its own creative process. The philosophical implications are profound. For all of human history, creation was a mystery relegated to mythology and speculation. Now we can watch it happening. We can see the actual process that transforms raw cosmic material into worlds, chemistry into geology, potential into reality. Dr. Mary Wojtek, head of NASA's astrobiology program, reflects on the significance. PDS-70 shows us that planet formation isn't a rare miracle. It's what the universe does naturally, inevitably, abundantly. Worlds are being born across the galaxy right now, each one a potential stage for the even greater miracle of life. The discoveries at PDS-70 also highlight how much we still don't know. We can see planets forming, but we don't fully understand how. We can detect the chemistry, but we can't predict the outcome. We can watch the process, but we can't yet replicate it in our theories. This humility is perhaps PDS-70's greatest gift. It reminds us that the universe is far more creative and complex than our models suggest. Every assumption we've made about planet formation has proven either incomplete or wrong. Reality is stranger and more wonderful than we imagined. For the children looking up at the stars tonight, PDS-70 offers a profound message. Worlds are being born right now. In the constellation Centaurus, too faint for the naked eye but blazing in our telescopes, new planets are forming, new moons are condensing, new possibilities are emerging. The universe is not a static museum of ancient lights, but a dynamic, creative force, constantly bringing forth new worlds. Some of those worlds might harbour life, some might develop intelligence, some might one day build telescopes and look back at us, wondering about their own origins, just as we wonder about ours. The cosmic perspective is dizzying. Our galaxy contains roughly 400 billion stars. If even a fraction have protoplanetary disks like PDS-70's, then millions of planetary systems are forming right now. Across the observable universe, with its 2 trillion galaxies, the number of worlds being born at this moment is beyond comprehension. Dr. Deborah Fisher at Yale, who has spent her career hunting for exoplanets, offers perspective. When I started in this field, we didn't know if other planets existed. Now we're watching them being born. In one generation, we've gone from wondering if we're alone to knowing that the universe is pregnant with worlds. PDS-70 isn't just showing us how planets form, it's showing us that we're part of a cosmic baby boom that's been happening for billions of years and will continue for trillions more. But perhaps the most profound impact of PDS-70 is personal. Every person who learns about this discovery must grapple with a fundamental shift in perspective. We are not the product of a unique miracle, but of a common cosmic process. Our world is not singularly special, but one of countless worlds. Our story is not separate from the universe, but woven into its fundamental fabric. This could be crushing or liberating, depending on your perspective. We're not uniquely chosen, but we're not alone either. We're part of something vast and creative and ongoing. Every star in the night sky might host worlds. Every world might host wonders we can't imagine. Dr. Lisa Kaltenegger captures this beautifully. PDS 70 teaches us that the universe is in the business of making homes. Every dust grain gathering around that young star is potentially part of someone's future planet. Every molecule in those disks might one day be part of an ocean, an atmosphere, or even a living creature wondering about its origins. We're not watching abstract astrophysics, we're watching the universe preparing places for life. The images from PDS 70, those glowing orbs of gas and dust still gathering themselves into worlds, are more than scientific data. They're baby pictures of planets. They're ultrasounds of worlds in utero. They're the universe showing us its maternity ward, where the next generation of cosmic homes is being born. As our instruments improve, as we discover more systems like PDS 70, as we watch more worlds being born, we're not just advancing science. We're writing a new chapter in humanity's understanding of its place in the cosmos. We're not strangers in a hostile universe, but children of a cosmos that naturally, inevitably, wonderfully creates worlds. PDS 70 will be remembered not just as the first photographed planet formation, but as the moment humanity truly understood that planet making is what the universe does. Stars make planets like trees make fruit, naturally, abundantly, diversely. And just as every apple contains the seeds of future trees, every planet contains the potential for life, intelligence, and wonder. The child born today will grow up in a world where watching planets form is routine, where the birth of worlds is as observable as the birth of stars. They will never know the profound loneliness of thinking Earth might be unique. They will always know that the universe is full of worlds being born, growing, evolving.
What will we discover when we can watch not just planet formation, but the development of atmospheres, the condensation of oceans, the emergence of continents? When we can track a world from its birth in a disk like PDS 70's through the emergence of life? When we can watch the universe not just making worlds, but making homes? These questions would have been pure fantasy just decades ago. Now they're research programs with funding and timelines. PDS 70 has turned science fiction into science planning. The final image from our story is not of PDS 70 itself, but of the thousands of astronomers, engineers and dreamers working to understand it. In control rooms and observatories, in universities and research centres, humans are dedicating their lives to understanding how worlds are born. They're writing the software to process the data, building the instruments to see farther and clearer, developing the theories to explain what we observe. They're doing this not because it has immediate practical benefits, but because this is what conscious beings do. We seek to understand our origins. We look for our cosmic context. We try to grasp our place in the magnificent, terrifying, wonderful process of cosmic evolution. PDS 70 has given us that context. We now know that we live on a planet that formed through processes we can observe happening elsewhere. We're made of materials that we can see gathering in protoplanetary disks. We emerged from violence and chaos that we can watch playing out 370 light-years away. This is not just scientific knowledge, it's existential revelation. It's the universe showing us our own baby pictures, letting us see where we came from, helping us understand what we are. We are the products of cosmic creation, witnesses to ongoing creation, and perhaps participants in future creation. As we develop the ability to detect and maybe communicate with worlds that formed like ours, as we perhaps one day learn to trigger planet formation ourselves, we transition from passive products of cosmic evolution to active participants in it. PDS 70 marks that transition. It's the moment we stopped just living on a planet and started understanding how planets come to be. It's the moment we stopped just wondering about our origins and started watching origins happen. It's the moment the universe became not just our home, but our comprehensible home. The planets forming around PDS 70 will take millions of years to finish growing, billions of years to potentially develop life. We won't see the end of their story, but we've seen their beginning, and that's enough to change our entire understanding of beginnings everywhere. Somewhere in the galaxy right now, on a planet that formed billions of years ago through processes just like what we observe at PDS 70, Intelligent beings might be pointing their instruments at a young star, watching new planets form, having their own revelations about cosmic creativity. We're all part of the same process, matter organizing itself to the point where it can observe matter organizing itself. This recursion, the universe creating observers who observe the universe creating observers, might be the deepest meaning we can extract from PDS-70. We're not separate from cosmic evolution, but its current expression. Through our eyes and instruments, the universe is watching itself create new worlds. What could be more profound than that? What could be more meaningful than being the universe's way of understanding its own creativity? PDS-70 is 370 light-years away. The light we see from it left when Galileo was perfecting his telescope. In a sense, we're looking at the past, but in another sense, we're looking at the eternal present of cosmic creation. A process that was happening billions of years before PDS-70 is happening there now, and will continue happening billions of years after PDS-70's planets have formed and died. We are witnesses to eternity. Through PDS-70, we see not just how our world formed, but how all worlds form. We see not just our past, but the universe's continuous present. We see not just distant planets being born, but the fundamental creativity that makes existence meaningful. This is the gift of PDS-70. It shows us that we're part of something magnificent. Every atom in our bodies, every thought in our minds, every dream we've ever had exists because 4.6 billion years ago, dust grains stuck together in a disk around a young star. We are the universe's way of turning dust into dreams, and right now, around PDS-70 and thousands of other young stars, more dust is gathering, more worlds are forming, more stages are being set for future dreams we can't imagine. The universe is not done creating, it's just getting started, and for the first time, we can watch it work. That bright spot in the disk around PDS-70, that glowing, gathering ball of gas and dust that will become a world, carries the same potential that Earth carried 4.6 billion years ago. The potential for oceans and continents, for life and intelligence, for beings who will one day look up at their night sky and wonder where they came from. Thanks to PDS-70, we no longer have to wonder. We know, we can see it happening. We are watching creation itself.